Imagine if history had unfolded differently. Imagine a cold winter morning in early 1945, somewhere in the chaos of a collapsing Reich. Picture a scene that never happened, but could reveal profound truths about the technological chasm that separated the Axis and Allied powers. The frost clings to the tarmac at Rechlin Air Base, Germany's premier testing facility for captured enemy aircraft. A group of Luftwaffe test pilots, their breath visible in the frigid air, stand before something impossible, something that shouldn't be here. A Boeing B-29 Superfortress, 4 massive radial engines, a wingspan stretching over 99 feet, silver aluminum skin gleaming in the weak winter sun. In our imagined history, this particular Superfortress, tail number 4, 2-65378, had been forced down over neutral territory during a hypothetical bombing mission gone wrong. Through a series of unlikely diplomatic exchanges and clandestine operations, it found its way into German hands. The crew had been interned. The aircraft remained intact. Hauptmann Werner Baumbach, one of Germany's most experienced test pilots, circles the bomber slowly. He has flown everything the Luftwaffe produced. He tested the Messerschmitt 262 jet. He evaluated captured British Spitfires and American P-47 Thunderbolts. But this machine represents something entirely different. This is not a fighter. This is a strategic weapon, a flying fortress designed to carry 10 tons of bombs across an ocean. Gentlemen, Baumbach says to his fellow pilots, whatever we find inside this aircraft will tell us everything we need to know about why we are losing this war. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The first thing that strikes the German engineers is the sheer scale of the Wright R-3350 duplex cyclone engines. Each power plant weighs nearly 3,000 pounds. 18 cylinders arranged in 2 rows. 54.9 litres of displacement. And according to the technical manuals they discovered in the aircraft, each engine produces 2,200 horsepower at takeoff power. 2,200 horsepower. Oberingenieur Klaus Hoffmann, chief engineer at Rechlin, stands before the number 3 engine with a measuring tape and a notepad. He has spent his entire career designing and testing German aviation engines. The Daimler-Benz DB605, the BMW 801, the Junkers Jumo 211. He knows their strengths. He knows their limitations. And now, looking at this American engine, he knows something else. Germany is years behind. The BMW 801 that powers the Focke-Wulf 190 produces, in its best variants, perhaps 1,700 horsepower for brief periods. The Daimler-Benz DB605 that drives the Messerschmitt 109 generates at most 1,800 horsepower with methanol water injection. These are sophisticated engines, the product of decades of German engineering excellence, but they are not this. Hoffmann orders the engine cowling removed. What he sees inside changes everything he thought he knew about American industrial capability. The supercharger is enormous, feeding compressed air to all 18 cylinders with brutal efficiency. The cooling system uses a sophisticated arrangement of baffles and ducting that manages heat far more effectively than anything in German service. The reduction gearing that connects the engine to the propeller is machined to tolerances that seem almost impossible. "How are they producing these?" asks his assistant, a young engineer named Schmidt. "How are they building engines like this in the quantities needed to equip hundreds of these bombers?" Hoffmann doesn't answer immediately. He's staring at the engine mount, noting how the entire power plant can be removed as a single unit. Modular, efficient, designed for mass production and rapid field replacement. "They're not building them," he finally says. "They're manufacturing them. There's a difference." In Germany, even by 1945, aircraft engines are still partially handcrafted. Skilled workers carefully assemble each component. Tolerances are checked manually. Production numbers are measured in hundreds, perhaps low thousands for the most common types. But this American engine shows signs of true mass production. Standardized parts, automated machining, quality control built into the manufacturing process rather than added at the end. The Americans aren't making engines, they're stamping them out like automobiles. The test pilots begin their examination of the cockpit. What they find is almost shocking in its sophistication. The pilot and co-pilot sit in a pressurized cabin, comfortable, spacious, with excellent visibility through large plexiglass panels. The instrument panel is logically arranged, clearly labeled, designed for long-duration missions flown at high altitude. Baumbach settles into the pilot's seat. He has flown pressurized aircraft before. The high-altitude reconnaissance versions of various German types used cabin pressurization, but never like this, never this refined. The entire forward and rear crew compartments of the B-29 are pressurized, connected by a long tunnel over the bomb bay. 11 crew members can operate in shirt-sleeve comfort at 30,000 feet. By contrast, German bomber crews wear heavy flight suits and oxygen masks. They fight the cold. They struggle with frost on instruments. They endure. The Americans, apparently, decided endurance wasn't necessary. They simply engineered the problem away. The flight controls feel smooth under Baumbach's hands, hydraulically boosted. The control yoke moves with minimal effort. He thinks of the Heinkel 177, Germany's only operational heavy bomber, which requires physical strength to maneuver at high speeds. He thinks of the constant control forces, the fatigue that sets in during long missions. This American bomber would be almost pleasant to fly, but it's the remote-controlled gun turrets that truly astound the German engineers. The B-29 carries 12 50-caliber machine guns arranged in 4 remote turrets, plus a tail position with a 20mm cannon. But the gunners don't sit at the guns. They sit at fire control stations, using computing gun sites linked to the turrets through a complex system of electric motors and analog computers. A single gunner can control multiple turrets. The system automatically corrects for airspeed, altitude, temperature, the ballistics of the ammunition. It's a level of fire control sophistication that seems almost science fiction to men accustomed to hand-aimed weapons. Hoffman spends hours examining the General Electric central fire control system. The wiring alone represents a technical achievement beyond anything in German service. Thousands of connections, miles of wire, all working together to give the B-29 defensive capabilities that would shred any conventional fighter attack. We couldn't build this, he admits to Baumbach that evening over ersatz coffee in the officers' mess. Not because we lack the theoretical knowledge. We couldn't build it because we lack the industrial infrastructure, the specialized components, the trained workforce, the time. Baumbach nods slowly. He's been thinking the same thing all day. The engine, he says, 2,200 horsepower. Do you know what that means for their entire air force? If they can produce engines like that in quantity, they can power anything. Heavy bombers, transport aircraft, they probably have engines even more powerful in development. He's right, though neither man knows it. By 1945, American engine manufacturers are already testing power plants producing over 3,000 horsepower. The Pratt & Whitney R-4360 Wasp Major, 28 cylinders, 4,300 horsepower. But even the R-3350 is enough to illustrate the gap. The Germans calculate the numbers. 4 engines, each producing 2,200 horsepower, give the B-29 a total of 8,800 horsepower at takeoff. The aircraft weighs over 100,000 pounds fully loaded, yet it can cruise at 220 miles per hour at 25,000 feet. It can reach over 350 miles per hour at altitude. Its range, with maximum fuel, exceeds 3,500 miles. Germany has nothing comparable. The Heinkel 177, powered by 2 coupled DB6-10 engines producing about 3,000 horsepower combined, carries less than half the bomb load over less than half the distance. It's slower, less reliable, and far more vulnerable to fighter attack. The Junkers Ju-390, a proposed heavy bomber, never proceeded beyond prototypes. The Focke-Wulf TAR-400, another heavy bomber project, was cancelled due to lack of resources and the obvious futility of competing with Allied strategic air power. By the time this hypothetical B-29 reaches Rechlin for testing, the strategic air war over Germany is already lost. The Luftwaffe is grounded by fuel shortages. Experienced pilots are dead. Production facilities are bombed to rubble. The technological superiority the Luftwaffe enjoyed in 1939 and 1940 has evaporated. But seeing the B-29 makes it visceral, makes it undeniable. On the third day of examination, the engineers attempt to start one of the Wright R-3350 engines. They've studied the manuals, worked through the procedures, verified the fuel and oil systems. Baumbach sits in the pilot's seat. Hoffmann stands beside the number 3 engine with a fire extinguisher, just in case. The engine coughs once, twice, then roars to life with a deep, powerful rumble that shakes the entire aircraft. Baumbach advances the throttle carefully. The propeller spins faster. The engine note rises. The power is intoxicating. He glances at the manifold pressure gauge. Even at idle settings, the engine feels more powerful than a DB605 at cruise power. He can only imagine what war emergency power would feel like. 59 inches of manifold pressure, 2,400 horsepower per engine. The aircraft would surge forward like a fighter, despite weighing 50 tons. After 10 minutes, he shuts it down. The engineers swarm the engine, checking for problems, looking for weaknesses. They find none. The engine ran smoothly, coolly, efficiently, built to operate for hundreds of hours between overhauls. That night, Baumbach writes a detailed report for Luftwaffe High Command. He chooses his words carefully. The war is lost. Everyone knows it. But the magnitude of Germany's technological deficit needs to be documented, needs to be understood. The American B-29 Superfortress represents a leap in aviation technology that Germany cannot match with current resources, he writes. The Wright R-3350 engine alone demonstrates engineering and manufacturing capabilities beyond our current industrial capacity. Each engine produces 2,200 horsepower reliably and repeatedly. Germany's best engines struggle to reach 1,800 horsepower under boost conditions and for limited duration. He continues, but the engine is merely one component. The aircraft's pressurization system, fire control computers, remote gun turrets, and overall integration represent a level of systems engineering that suggests the Americans have moved beyond traditional aircraft design into a new paradigm. They are building machines that operate as unified systems rather than collections of individual components. Most significantly, this is not a prototype. This is a production aircraft, one of hundreds, perhaps thousands. The Americans have achieved mass production of advanced technology at a scale Germany never attempted. This represents not merely a technological advantage, but an industrial and systemic superiority that cannot be overcome through tactical or operational innovation. The report travels up the chain of command. In our imagined history, it reaches Hermann Göring's desk. The Reichsmarschall reads it once, then throws it in the trash. More defeatist nonsense, he mutters. German engineering is the finest in the world. But Baumbach's report is not defeatist. It's realistic. And the reality is stark. The examination of the B-29 continues over the following weeks. Each day reveals new layers of American engineering sophistication that leave the German team increasingly sobered. Hoffmann focuses on the materials. The aluminum alloys used in the airframe are lighter and stronger than comparable German materials. The plexiglass in the cockpit windows is optically superior, providing better visibility with less distortion. Even the rubber in the fuel lines shows advanced polymer chemistry that resists degradation better than German equivalents. It's not just one thing, he explains to his team during a morning briefing. It's everything. Every single component shows incremental improvements over what we use. Individually, each improvement is small, but combined across an entire aircraft, the cumulative effect is enormous. Schmidt, The young engineer raises a hesitant hand. Sir, could we not simply copy what we see here? Reverse engineer the critical systems? Hoffman sighs. It's a question he's been dreading. In theory, yes. In practice, no. Let me show you why. He leads the team to the engine again. The cowling is off, exposing the complex machinery inside. This supercharger, he says, pointing to the massive unit bolted to the rear of the engine. To manufacture this, you need specialized casting equipment capable of producing complex shapes with precise internal passages for airflow. You need metallurgy expertise to create alloys that can withstand high temperatures and pressures. You need quality control systems to ensure every unit meets specifications. He moves to the propeller. This is a Hamilton Standard constant-speed propeller. 4 blades, each precisely manufactured and balanced. The governor system that controls blade pitch is itself a marvel of mechanical engineering. To copy this, we would need to understand not just what it does, but how it achieves it. The internal mechanisms, the materials, the manufacturing processes. And then, he continues, his voice growing quieter, we would need to build the factories to manufacture these components. We would need to train workers, establish supply chains, create quality assurance systems. Even if we started today, even if the war wasn't lost, we would need years, perhaps a decade. The Americans, meanwhile, have been refining these systems since the late 1930s. The R-3350 first ran in May of 1937. By the time it entered service in the B-29 inches, 1943, it had undergone 6 years of development and testing. Even then, it had problems: engine fires, valve failures, cooling issues. But the Americans had the resources to solve these problems while simultaneously mass-producing the engines. By 1944, they were building thousands of R-3350 annually. Chrysler alone produced 18,000 engines. Wright Aeronautical produced another 13,000. Over 30,000 engines total, each one representing 2,200 horsepower of reliable power. Germany, by contrast, struggled to produce thousands of engines total across all types. The DB605, the most produced German engine of the late war, saw perhaps 42,000 units built throughout its entire production run. But these engines were smaller, less powerful, and required more maintenance. The Americans weren't just ahead, they were operating in a different industrial dimension, entirely. Baumbach arranges for a test flight. It takes weeks to prepare. The aircraft needs fuel, and aviation gasoline is scarce in Germany by early 1945. The systems need to be thoroughly checked. Ground crews need to be trained on procedures they've never seen before. Finally, on a cold morning in February, the bomber is ready. Baumbach climbs into the left seat. His co-pilot, Major Ernst Kupfer, settles into the right seat. A flight engineer, radio operator, and 2 gunners complete the minimal crew. They're flying without bombs, with reduced fuel, testing only the aircraft's basic flight characteristics. The startup procedure is complex but logical. Each engine fires in sequence. Number 3. Number 4. Number 2. The sound is incredible. 8,800 horsepower idling on the tarmac, propellers spinning slowly, the entire aircraft vibrating with restrained power. Baumbach advances the throttles for takeoff. The big bomber accelerates smoothly down the runway. At 80 knots, he eases back on the yoke. The nose lifts. At 110 knots, the B-29 breaks ground, climbing steadily despite weighing over 70,000 pounds. Unglaublich, Kupfer breathes. Incredible. The climb performance is remarkable. Even at reduced power settings to conserve fuel, the B-29 ascends at over 1,000 feet per minute. Baumbach levels off at 15,000 feet and begins exploring the aircraft's handling characteristics. The controls are light, responsive. The hydraulic boost makes maneuvering effortless compared to German heavy aircraft. He banks left, then right. The big bomber rolls smoothly, precisely. He pulls back gently, raising the nose. The aircraft climbs willingly. He pushes forward, descending. No unusual control forces, no unexpected behavior. "It flies like a fighter," he says, though that's not quite accurate. It flies like nothing he's experienced. A large aircraft that handles with the taper AC precision of a much smaller one. He runs through some basic performance tests. Cruise speed at 15,000 feet, at normal power, 220 miles per hour. Fuel consumption, reasonable for the power being produced. Engine temperatures, all in the green. Oil pressure, stable. He imagines this aircraft at full combat weight, at 25,000 feet, on a mission to Berlin from England, or better yet, from the Mariana Islands to Tokyo. 3,000 miles there and back, 10 tons of bombs, pressurized comfort for the crew, defensive firepower that could destroy entire fighter formations. The Germans have nothing that could stop a mass formation of these bombers. The Me-262 jet might catch them at altitude, but jet operations are limited by fuel and reliability. Conventional fighters lack the performance to intercept effectively at operational altitude. The flak guns could reach them, but accuracy at extreme altitude is poor. Most critically, even if Germany could shoot down B-29 seconds, the Americans could replace them faster than they could be destroyed. The industrial mathematics are brutal and unavoidable. After 90 minutes, Baumbach brings the bomber back to Rechlin. The landing is smooth, almost gentle. The wide-track landing gear makes ground handling straightforward. He taxis to the parking area and shuts down the engines one by one. The flight was perfect. Not a single system malfunction. Not one moment of concern. The aircraft performed flawlessly. That's what frightens him most. This isn't a temperamental prototype being coaxed through a test flight. This is a mature, reliable weapon system being operated by pilots who barely know it. Imagine what it could do in experienced American hands. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The engineers conduct further tests over subsequent weeks. They examine the bomb bay, noting its capacity and flexibility. They study the defensive armament, test firing the remote turrets at ground targets. They analyze the fuel system, the hydraulics, the electrical system, the oxygen system for high-altitude operations. Every examination reveals the same pattern: American pragmatism combined with engineering excellence. Nothing is over-designed, nothing is under-designed. Every system is optimized for its specific purpose, then integrated seamlessly with every other system. The Germans find themselves grudgingly admiring their enemies. This is not crude mass production. This is sophisticated manufacturing applied at tremendous scale. The Americans have somehow achieved both quality and quantity simultaneously, something German industry struggled to accomplish even before the bombing campaign destroyed production capacity. Hoffmann writes his own technical report, hundreds of pages documenting every aspect of the R-3350 engine. His conclusions are stark. The Wright R-3350 represents the culmination of nearly a decade of focused development, he writes. Its 2,200 horsepower output is achieved through a combination of factors: large displacement, efficient supercharging, advanced metallurgy, and sophisticated cooling. Each factor alone would be achievable by German industry. Combined, they represent a level of systems integration that Germany has not mastered. More concerning is the reliability. This engine is designed to operate for hundreds of hours between major overhauls. German engines typically require more frequent maintenance and have shorter operational lifespans. The Americans have prioritized durability and maintainability, understanding that operational availability is as important as peak performance. Finally, the manufacturing quality is exceptional. Every component shows precise machining, careful assembly, and thorough inspection. This is not handcrafted excellence, but industrial precision. The Americans have systematized quality, rather than relying on individual craftsmen's skill. This approach allows scaling to massive production volumes while maintaining standards. His report concludes with a paragraph that could serve as an epitaph for German aviation ambitions. The technological gap between German and American aviation engines is not primarily one of knowledge or theory. It is a gap in industrial capacity, manufacturing sophistication, and resource availability. Germany could potentially design an engine comparable to the R-3350. But Germany cannot manufacture such engines in the quantities required, using the materials available, with the workforce remaining. The war has been lost not because German engineers failed, but because German industry could not compete with American industrial might. By March of 1945, the examination of the B-29 is complete. The aircraft sits in a hangar at Rechlin, a trophy that serves only to highlight Germany's defeat. Baumbach and Hoffmann both know the war will end within weeks. The Red Army is approaching from the east. American and British forces are crossing the Rhine in the west. They discuss the aircraft's fate one evening. Should we destroy it? Baumbach asks. Prevent it from falling into Soviet hands? Hoffmann considers. Would it matter? The Soviets will capture German factories, German engineers, German documents. They'll learn everything we know, which is considerably less than what the Americans know. One B-29 more or less won't change their technological trajectory. Besides, he adds with a bitter smile, perhaps they should have it. Perhaps they should see what we saw. Understand what we're up against. The war with Germany is ending, but the competition between the Soviets and the Americans? That's just beginning. And based on this aircraft, I know who I'd bet on. In our imagined history, the B-29 remains at Rechlin until Soviet forces overrun the base in April. They find the aircraft intact, along with extensive German technical notes and test reports. These documents and the aircraft itself eventually make their way to Moscow, where Soviet engineers examine them with the same growing realization that overwhelmed their German counterparts. The Americans can do things we cannot, not because they're smarter, but because their system works better. The Wright R-3350 engine becomes a measuring stick, a benchmark. 2,200 horsepower, reliably produced in massive quantities, installed in thousands of aircraft that are themselves marvels of engineering and manufacturing. In the real history we know, the Soviets eventually captured 3 actual B-29 seconds that made emergency landings in Soviet territory after bombing Japanese targets in 1944. Stalin ordered the aircraft reverse-engineered, resulting in the Tupolev Tu-4. Even with access to actual B-29 seconds and intensive effort, the Soviet copy took years to develop and never quite matched the original's capabilities. If Germany had captured a B-29 and attempted the same process, the results would have been even less successful. The industrial base wasn't there. The material resources weren't available. The time didn't exist. The examination would have revealed only what German engineers already suspected but couldn't quite admit. The war was lost, not on battlefields, but in factories. American industrial capacity, built over decades and protected by oceans, produced weapons that Germany simply couldn't match. The R-3350 engine, with its 2,200 horsepower and sophisticated engineering, symbolized everything Germany lacked. Not brilliance, German engineers were brilliant. Not dedication, German workers were dedicated. But scale, resources, industrial depth, the ability to develop advanced technology and then manufacture it by the thousands, while simultaneously producing everything else needed to fight a global war. The story of this imagined examination reveals deeper truths about technological competition and industrial warfare. The German pilots and engineers at Rechlin weren't stupid. They weren't blind to their own shortcomings. But confronting the B-29 and its massive Wright R-3350 engines forced them to acknowledge realities they had tried to rationalize away. Consider the development timeline. The R-3350 first ran in May of 1937, more than 2 years before the war began. By the time the B-29 entered service in mid-1944, the engine had undergone 7 years of continuous development, 7 years of testing, refinement, problem-solving, and improvement. Germany, by contrast, spent those same years fighting a war that consumed resources and attention. The Daimler-Benz DB605 entered service in 1942 and immediately faced material shortages. Nickel for exhaust valves became scarce. Chrome plating had to be substituted. Engineers made compromises, trading peak performance for availability of materials. The Americans didn't have to make those compromises. They had access to chromium from South Africa, nickel from Canada, aluminum from plants across the United States, copper for wiring, steel for crankshafts. Every exotic material needed for advanced engine construction flowed into American factories without interruption. More importantly, American factories weren't being bombed. Wright Aeronautical's plant in New Jersey operated around the clock, producing R-3350 engines by the hundreds each month. Workers arrived on schedule. Raw materials arrived on trains that ran on time. Electricity powered the assembly lines without interruption. Meanwhile, German engine plants operated under constant threat. Allied bombing raids destroyed factories, killed workers, disrupted supply chains. The Daimler-Benz plant at Stuttgart was repeatedly bombed. The BMW facility at Munich suffered devastating raids. Production schedules became meaningless when you couldn't predict whether the factory would still exist next week. The hypothetical German examination of the B-29 would have made these disparities impossible to ignore. Every rivet in that aircraft represented secure supply chains. Every wire represented uninterrupted copper production. Every engine represented 7 years of peaceful development followed by massive-scale manufacturing. Baumbach understood this instinctively. He had been a bomber pilot before becoming a test pilot. He knew what it took to conduct sustained strategic bombing campaigns. He had seen German industry systematically dismantled by Allied air power, while German bombers lacked the range, payload, and numbers to retaliate effectively. The B-29 represented the kind of strategic air power Germany never developed, because Germany never needed to bomb targets 3,000 miles away. Germany fought continental wars. Its bombers needed range measured in hundreds of miles, not thousands. The Heinkel 111 could reach London from French bases. That was sufficient for Germany's strategic goals in 1940 and 1941. But when those goals shifted, when Germany needed to strike Soviet industry beyond the Ural Mountains or pressure American war production across the Atlantic, the Luftwaffe had nothing. No heavy bomber fleet, no ultra-long-range capability, no tradition of strategic bombardment. The Americans had spent the 1930s thinking about exactly these problems. How do you project air power across oceans? How do you bomb targets in Japan from bases in China or the Marianas? How do you create a bomber that can fly 3,000 miles, fight off interceptors, and return home? The answers led directly to the B-29, pressurized crew compartments for high-altitude operations, remote-controlled gun turrets for efficient defense, the most powerful production engines in the world, sophisticated navigation and bombing systems. Everything integrated into a single airframe designed from the start for long-range strategic missions. By the time German engineers examined this hypothetical captured B-29, these questions seemed almost quaint. Strategic bombardment wasn't theoretical anymore. It was happening over Germany every day. Hundreds of American B-17 seconds and B-24 seconds escorted by swarms of fighters obliterated German cities and industry. The Luftwaffe, which had dominated European skies in 1940, was reduced to desperate defensive measures by 1945, and the B-29 seconds weren't even needed over Germany. The Americans had sufficient bomber forces in Europe using older, shorter-range designs. The B-29 seconds were reserved for the Pacific, where their unique capabilities were essential. That spoke volumes about American industrial depth. They had multiple fleets of strategic bombers, each numbering in the thousands. They could afford to dedicate their most advanced bomber exclusively to one theatre, while fighting effectively in another theatre with earlier designs. Germany built just over 1,000 Heinkel 177s, its only operational four-engine heavy bomber, total production across 6 years of war. The Americans built nearly 4,000 B-29 seconds in less than 2 years, and that was in addition to tens of thousands of B-17 seconds, B-24 seconds, and other bomber types. The mathematics of industrial warfare are unforgiving. Germany's entire aircraft production for all of 1944, approximately 40,000 aircraft of all types, roughly equaled American production of heavy bombers alone. When you added American fighters, medium bombers, transports, trainers, and naval aircraft, American production reached nearly 100,000 aircraft in 1944. One country, 100,000 aircraft. In a single year, the B-29's Wright R-3350 engines were just one component of this industrial miracle, but they exemplified the whole. Advanced technology, mass-produced, deployed globally, and continuously improved. The early R-3350 seconds had problems. Engines caught fire, cylinders overheated. But American engineers fixed these issues while production continued. By late 1944, the R-3350 was reliable enough for continuous combat operations across the vast Pacific. German engineers would have been appalled and impressed in equal measure, appalled at their own industry's inability to match this performance. Impressed by the sheer audacity of American manufacturing scale, Hoffman's technical analysis would have noted specific innovations. The R-3350 used a sophisticated cooling system with carefully designed baffles directing air over each cylinder. The supercharger employed a 2-speed drive system, allowing optimal performance at different altitudes. The reduction gearing connecting engine to propeller used helical gears for smooth power transfer and reduced noise. Each innovation represented years of research and development. Each required specialized manufacturing equipment. Each needed skilled workers who understood the theory behind the practice. The Americans had all of these elements. German industry, hollowed out by war and bombing, had few. But perhaps most impressive was the maintenance philosophy. The R-3350 was designed for field maintenance. Major components could be replaced relatively quickly. The modular construction allowed engines to be swapped out entirely if necessary. Technical manuals were clear, detailed, and written for mechanics with good but not extraordinary skills. German engines, particularly late-war variants, often required specialists for major maintenance. The tolerances were tight. The procedures were complex. A mechanic who understood the BMW 801 might struggle with the Jumo 211. Training was inconsistent. Documentation was sometimes contradictory. The Americans standardized everything. Every R-3350 was built to the same specifications. Every mechanic trained on the same manuals. Every base stocked the same. Spare parts. This boring, unglamorous systematization made the difference between an aircraft fleet that could sustain operations and one that couldn't. By March of 1945, when our imagined examination concluded, these lessons were academic. The war was ending. Germany's defeat was certain. But the knowledge gained from examining the B-29 and its engines would inform post-war thinking about aviation and industrial development. Many German engineers and scientists would eventually work for the Allied powers after the war. Some went to America through Operation Paperclip. Others were taken by the Soviets through Operation Osoaviakim. They brought with them hard-won expertise in aeronautics, rocketry, and jet propulsion. But they also brought humility. The examination of American technology, whether actual captured aircraft or intelligence reports, had taught them that genius alone doesn't win wars. Organization wins wars. Industrial capacity wins wars. The ability to transform scientific knowledge into thousands of operational weapons wins wars. The Soviet Union learned these lessons and reverse-engineered the B-29 into the Tupolev Tu-4. But even with 3 actual B-29 seconds to study, even with German expertise to assist, the Soviet copy took until 1947 to fly and never quite matched the original's reliability and performance. If Germany had captured a B-29 inches 1945 and somehow survived to attempt copying it, the results would have been even less successful. The industrial base was destroyed. The material resources were exhausted. The skilled workforce was depleted. And most critically, Germany lacked the peace and stability needed for sustained development work. The hypothetical examination of the B-29 at Rechlin would have been an epitaph for German military-industrial ambitions. A moment of clarity when experienced pilots and engineers confronted the magnitude of their defeat, not in battlefield reports, but in rivets and cylinders and wiring harnesses. Baumbach would have understood this. He was an intelligent man who had seen enough of war to recognize its realities. The B-29 wasn't just a bomber, it was a message, a demonstration of what American industry could achieve when fully mobilized. And the message was clear. You cannot win this war. You never could have won this war. The disparity was too great from the beginning. The Wright R-3350 engine, spinning its massive propeller at 2,600 revolutions per minute, producing 2,200 horsepower hour after hour, represented industrial civilization at its peak. Metallurgy, thermodynamics, mechanical engineering, quality control, mass production, all combined into 18 cylinders of refined power. Germany had brilliant engineers who understood the theory. But theory without industrial capacity produces only prototypes and paper designs. The Americans turned theory into 18,000 engines. That's the difference between an advanced nation fighting for survival and an industrial superpower operating at full capacity. In the quiet moments after test flights, Baumbach would have sat in the pilot's seat of the captured B-29 and thought about parallel histories. What if Germany had focused on heavy bombers instead of tactical air power in the 1930s? What if German industry had been organized for mass production instead of craft manufacturing? What if the resource base had been larger, the geography more favorable, the strategic situation less desperate? But these what-ifs led nowhere. History unfolded as it did. Germany lost. America won. And the B-29 with its massive R-3350 engines flew countless missions over Japan, eventually delivering atomic weapons that ended the war entirely. The examination at Rechlin, in our imagined history, would have been forgotten in the chaos of Germany's final collapse. The test reports would have been lost or destroyed. The pilots and engineers would have scattered, some dying in the war's final weeks, others captured by advancing Allied forces, a few escaping to uncertain post-war fates. But the knowledge would have lingered, the understanding that technological competition isn't just about innovation, but about the industrial systems that transform innovation into operational capability. That brilliance matters less than capacity, that the nation with secure resources, intact infrastructure, and decades of industrial development holds advantages that tactical genius cannot overcome. The B-29 flew on into the post-war era. Modified versions served in the Korean War. The Boeing B-50, essentially an upgraded B-29, remained in service through the 1950s. The basic design informed later Boeing products, including the successful 307 and 707 commercial airliners. The Wright R-3350, improved with turbo-compound systems, powered civilian aircraft well into the 1960s. These aircraft and engines represented a lineage of American aviation development that stretched back decades and forward into the jet age. Continuous improvement, sustained investment, industrial depth, all the things Germany lacked when it needed them most. If German pilots had examined a captured B-29 inches 1945, their conclusion would have been inescapable. We were years behind. Not years behind in starting the race, but years behind in industrial development, resource access, and systematic approach to technology. The gap couldn't be closed through heroic effort or tactical brilliance. It was structural, fundamental, decisive. and the Wright R-3350 engine, with its 2,200 horsepower reliably delivered, would have symbolized that gap perfectly. Not the most powerful engine ever built, not the most sophisticated, but powerful enough, sophisticated enough, and produced in quantities large enough to equip a fleet of strategic bombers that changed warfare forever. That's what German engineers would have seen when they examined those 18 cylinders, not just metal and fire, but the industrial capability of a rival they could never match. A sobering lesson in the mathematics of modern war, where production capacity often matters more than tactical skill, and where the nation with the deepest industrial base usually prevails. The hypothetical examination would have ended with Hoffman writing one final sentence in his report, a sentence that captured the essential truth. The Americans did not build a better bomber through superior engineering alone. They built a better bomber because they possessed superior capacity to transform engineering into reality, at scale, under pressure, without compromise. That capacity, industrial, organizational, material, decided the war as surely as any battle. The B-29 and its R-3350 engines were simply the most visible proof. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. February 17th, 1944. The lagoon at Truk burns under a tropical sky turned black with smoke. Inside the bridge of USS Iowa, moving at 32 knots through azure waters that had been, until hours ago, Japan's untouchable fortress, Captain John McCrae stands before the plotting table. The numbers coming through are staggering. Carriers have already sunk dozens of merchant ships, 250 Japanese aircraft destroyed on the ground or in the air. But now, something different. A group of warships fleeing north through the passes. Admiral Raymond Spruance, commander of the Fifth Fleet, has made a decision that surprises even his own staff. He wants a surface action. The light cruiser Katori, destroyers Maikaze and Nowaki, the auxiliary cruiser Akagi Maru. Already battered by carrier aircraft, they're running for their lives, and Iowa, along with her sister New Jersey, is being unleashed to finish them. What happens in the next 2 hours will set attempts of the Sephard record that stands to this day, the longest-range engagement between battleships and surface vessels in naval history. But more than that, it will demonstrate something the Japanese High Command had never fully grasped. American battleships didn't just have bigger guns or thicker armor. They had something far more dangerous, the ability to hit what they aimed at from distances previously thought impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why the engagement at Truk represented such a shock to Japanese naval thinking, you have to go back to how both navies understood battleship combat. For decades, perhaps since the Battle of Tsushima in 1905, the Imperial Japanese Navy had built its entire strategic doctrine around a concept called Kantai Kessen, the decisive battle, one enormous fleet action where Japanese battleships, manned by superior trained crews imbued with fighting spirit, would close to medium range and destroy the American battle line through courage, skill, and the weight of their shells. Range wasn't just a technical specification, it was wrapped up in an entire philosophy of warfare. Japanese naval theorists believed that battles would be decided at ranges of perhaps 10 to 15 miles, close enough for optical rangefinders to be effective, close enough for the human element, crew training, and fighting spirit to matter decisively. The idea that shells could be accurately placed on target from beyond the horizon, from distances where the enemy ships couldn't even be seen with the naked eye, seemed more theoretical than practical. This wasn't ignorance. Japanese naval intelligence was extensive and professional. They knew, in general terms, what American battleships could do on paper. They knew the specifications: range, shell weight, armor thickness. What they didn't fully appreciate, what they couldn't quite believe until they saw it with their own eyes, was the fire control. American radar-directed fire control systems, particularly the Mark 8 fire control radar mounted on the Iowa-class battleships, represented a revolution in naval gunnery. While Japanese warships still relied primarily on optical rangefinders, impressive devices in their own right but fundamentally limited by visibility, weather, and distance, American battleships could calculate firing solutions in conditions where the target was barely visible, or not visible at all. The system worked like this. Radar detected the target and provided continuous range and bearing data. This information fed directly into an analog computer, a mechanical marvel called a rangekeeper. The rangekeeper factored in not just the target's position, but its speed and course, the speed and course of the firing ship, wind direction and velocity, air temperature and density, even the rotation of the Earth. It calculated where the target would be by the time a shell, traveling for perhaps a minute and a half through a parabolic arc reaching heights of over 7 miles, finally arrived. This wasn't guesswork. It wasn't a salvo fired in hope. It was mathematics made lethal. And the Japanese, for all their intelligence gathering, had never quite internalized what this meant in practice. They had built the Yamato and Musashi, the largest battleships ever constructed, mounting 18-inch guns that could theoretically outrange anything afloat. But theoretical range and effective range are very different things. Without comparable fire control, those mighty guns were limited to distances where optical sighting might work. Meanwhile, American battleships, with smaller but better controlled 16-inch guns, could engage effectively at ranges the Japanese had never seriously practiced. The morning of February 17th began with carrier strikes. Task Force 58, under Admiral Mark Mitcher, unleashed wave after wave of aircraft against truck. The base had been, for 2 years, considered Japan's Gibraltar of the Pacific, a vast natural harbour protected by reefs and defended by hundreds of aircraft. American submarines had lurked outside, sinking ships that ventured out, but no one had dared a direct assault. Until now. By mid-morning, the lagoon was a graveyard. Merchant ships burned at anchor, destroyers and cruisers, caught unprepared, had been bombed and torpedoed. The air reeked of burning oil and cordite. Japanese pilots, scrambling desperately to defend their base, were being shot down by American fighters in numbers that presaged what would later be called the Great Marianas Turkey Shoot. Light cruiser Katori, serving as a training vessel, had been moored inside the lagoon. Her captain, Takao Saiji, recognized immediately that staying meant certain death. At 0430 hours, before the American strike even began, Katori had slipped out through the North Pass, accompanied by the auxiliary cruiser Akagi Maru, destroyers Maikaze and Nowaki, and the small mine-sweeping trawler Shonan Maru, number 15. They were running, hoping to reach Saipan, hoping the Americans would be too focused on targets inside the lagoon to notice a few ships making for open water. They almost made it. But American reconnaissance planes spotted them. Reports reached Admiral Spruance, commanding from the heavy cruiser Indianapolis. His carriers had wrought devastation inside the lagoon. Aircraft were returning, some damaged, all low on fuel and ammunition. The standard procedure would be to let them go. Japanese ships fleeing truck could be hunted by submarines, by aircraft from other bases. Spruance, however, wanted something else. He wanted a surface action. He wanted his battleships and cruisers to close with the enemy and engage ship to ship. Some of his staff thought it reckless. Carriers could finish the job safely. Why risk capital ships? But Spruance understood something. They didn't. This war was proving, again and again, that carriers had replaced battleships as the decisive arm of naval warfare. But that didn't mean battleships were useless. Not yet. And he wanted to demonstrate, both to his own navy and to the Japanese, that American surface ships could still fight and win decisively. He formed Task Group 50.9, battleships Iowa and New Jersey, heavy cruisers Minneapolis and New Orleans, 4 destroyers, light carrier cowpens providing air cover, and he put himself in tactical command. The chase was on. The Japanese ships had perhaps a 2-hour head start, They were running at close to their maximum speed, around 26 knots for Katori, 35 for the destroyers. But Iowa and New Jersey, the newest and fastest battleships in the American fleet, could make 33 knots, and they had radar. They didn't need to see their quarry to track them. Shortly after 1300 hours, American scout planes from Cowpens confirmed the Japanese position. Katori and her escorts were 30 miles northwest of Truk, heading roughly north, still running. On Iowa's bridge, Captain McCrea received updates from the Fire Control Center, range to target 32,000 yards, 18 statute miles. The Japanese ships were still invisible to the naked eye, hull down beyond the horizon, but on the radar scope, they were clear as day. 4 distinct contacts, moving steadily northeast. Admiral Willis Lee, commanding the battleship division, gave the order. Prepare for surface action. All ahead flank, increase speed to intercept. Below decks, in the massive turrets, gun crews went to work. Each turret, designated 1, 2, and 3, contained 3 16-inch guns, 9 guns total. Each barrel, 66 feet long from breech to muzzle. Each shell, for the armor-piercing rounds, 2,700 pounds, nearly 1.5 tons of steel and explosive, capable of punching through 2 feet of armor plate at 15 miles. The armor-piercing shells, designated Mark 8, were engineering marvels, a hardened steel cap at the tip to bite into armor, a ballistic cap to maintain velocity through the air. Inside, a relatively small bursting charge. These weren't designed to explode on contact like bombs. They were designed to penetrate deep into a ship's vitals, then detonate, destroying magazines, engineering spaces, command centers, killing the ship from the inside. For this engagement, though, the high-capacity shells, Mark 13, would be more suitable. 1,900 pounds, with a much larger bursting charge designed to create devastating fragmentation. Against lightly armoured ships like destroyers and the thin-skinned Katori, these were the rounds of choice. In the plotting room, the rangekeeper hummed. Inputs from radar, inputs from the ship's gyroscopic compass and speed indicators, the target's course and speed, estimated and continuously updated. The system calculated the firing. Solution: barrel elevation needed. Lead angle to account for the target's. Even the wear on the gun barrels, which slightly reduced muzzle velocity after repeated firings, was factored in. At 14,500 yards, Iowa opened fire. 7¼ statute miles. Turret 2 spoke first. 3 guns, 3 shells, each weighing nearly a ton, launched at a muzzle velocity of 2,600 feet per second. The recoil was enormous. The entire ship shuddered. The overpressure wave from the guns could injure unprotected personnel on deck. The blast deflectors, massive armoured plates designed to protect the decks from the gun muzzle's fury, glowed briefly from the heat. 45 seconds later, the first salvo arrived. Katori, already crippled by earlier air attacks, was attempting to manoeuvre. Her captain knew what was coming. 3 shells, arriving in a tight pattern. 1 fell short, 1 fell long. The third struck the water, alongside, showering the ship with fragments and spray. A straddle. The next salvo would adjust. Katori's crew fought back. Her 5-inch guns, designed for anti-aircraft work and defense against destroyers, opened fire. She even got off a torpedo salvo, a desperate, defiant gesture. But the range was too great. Her optical rangefinders couldn't get an accurate fix on ships hull down on the horizon. The torpedoes ran wild, missing New Jersey by hundreds of yards. Iowa fired again. And again. Each salvo was 3 shells, each salvo adjusted based on where the previous one had fallen. The rangekeeper updated continuously. The radar showed Katori's course changes, slight alterations as she tried to evade. But there was no evading. At these ranges, the shells took almost a full minute to arrive, but the fire control system predicted where the ship would be, not where it was. The fourth salvo hit. Multiple shells struck Katori's superstructure and midships. The 1,900-pound shells detonated with immense force. Fragmentation scythed through anything not protected by heavy armor, and Katori, a light cruiser, had very little heavy armor. Her bridge took a direct hit. Her engineering spaces were torn open. Fires erupted. The destroyer, Maikaze, her consort, tried to stand by, tried to lay smoke, tried, gallantly and uselessly, to draw fire from the dying cruiser. She launched torpedoes of her own at Iowa and New Jersey. Lookouts on New Jersey spotted the torpedo wakes. The battleship altered course slightly. The torpedoes passed just ahead of the bow. One officer later remarked that it would have been embarrassing to be hit, but Maikaze's sacrifice bought nothing. American heavy cruisers, Minneapolis and New Orleans, had closed the range. Their 8-inch guns added their weight to the barrage, and carrier aircraft from cowpens, circling overhead, warned the surface ships of any submarine threat and confirmed hits. Katori, her guns still firing even as she listed heavily, rolled over at 1,343 hours, 11 minutes under fire. Captain Saiji went down with his ship. Large groups of survivors were seen in the water. Destroyer Burns attempted to rescue some of them, but the Japanese sailors, trained to fight to the death, refused rescue. Some attacked the American sailors. In the end, none were pulled from the water. None survived. Every man aboard Katori, approximately 300 officers and crew, perished. Maikaze, still fighting, became the next target. Outgunned 20-1, she nonetheless closed to launch another torpedo attack. Minneapolis and New Orleans concentrated their fire. Shell after shell slammed into the 2,000-ton destroyer. She absorbed punishment that would have sunk 3 ships her size. Her crew fought until the magazine exploded and she broke in half. All hands lost. Destroyer Nowaki, seeing what had happened to her sister ships, made a run for it. She was faster than the battleships, capable of over 35 knots. And she had a head start. Iowa and New Jersey turned to pursue, range open to 34,000 yards, then 36,000, 19 miles, 20 statute miles, beyond the range where any battleship had ever scored a hit in combat. But the chase wasn't about hitting. It was about demonstrating capability. Iowa fired. New Jersey fired. Salvos arced out across the Pacific, shells climbing miles into the sky before plunging back down. At maximum elevation, 45 degrees, the trajectory was almost like an artillery piece firing over a mountain. The shells fell around Nowaki. One salvo straddled her, shells landing to port and starboard. Splinters from near misses caused casualties and minor damage, but she was too fast, too far, and pulling away. At 35,700 yards, 20.3 statute miles, New Jersey fired what would be the final salvo of the engagement. It was a straddle. One shell splashed into the ocean to Nowaki's port side, another to starboard. The destroyer disappeared into rain squalls and opened the range. She would escape, but the point had been made. 23 miles had been listed as the theoretical maximum range of the Iowa-class guns. 20.3 miles was the confirmed combat firing, the longest-range gunnery engagement between surface vessels ever recorded, a record that stands today and will likely stand forever, as no navy builds battleships anymore. The auxiliary cruiser Akagi Maru never even made it to the surface engagement. Carrier aircraft had caught her hours earlier, 3 direct bomb hits and massive internal explosions. She was abandoned and sinking by the time Iowa opened fire on Katori. The small minesweeping trawler Shonan Maru, number 15, tried to run, then tried to fight. Destroyer Burns dispatched her with 5-inch gunfire. Like Katori and Maikaze, there were no survivors. 4 ships, 1 escaped, 3 destroyed. In the span of 90 minutes, American surface vessels had demonstrated something that Japanese naval planners had never quite believed possible: accurate, devastating fire from ranges that exceeded anything in their doctrine, their training, or their experience. But here's where the story deepens. Because this wasn't just about range. It wasn't just about hitting ships from 20 miles away, though that was remarkable enough. What made the engagement at Truk truly significant, what made it a watershed moment in naval warfare, was what it revealed about the fundamental assumptions underlying Japanese naval strategy, and how catastrophically wrong those assumptions had been. The Imperial Japanese Navy had not been complacent. They had not been ignorant. They had studied their potential enemy extensively. Japanese naval attaches in Washington before the war had filed detailed reports. They knew the specifications of American battleships. They knew about radar. They knew, in technical terms, what the systems could do. What they didn't grasp, what they couldn't quite internalize until it was demonstrated in combat, was the magnitude of the advantage these systems conferred. Consider the math. In a traditional gunnery engagement, using optical rangefinders, a battleship might need to fire 20, 30, even 40 salvos to score hits on a maneuvering target at extreme range. The first salvos were for ranging, finding the distance. Then corrections for wind, for the target's speed and course. The process was iterative, slow, and consumed enormous amounts of ammunition, and it only worked if you could see the target clearly. The Mark 8 fire control radar, combined with the Rangekeeper analog computer, collapsed this process. The first salvo might miss, but the second or third would straddle, and the fourth would hit. Iowa had fired 46 16-inch shells at Katori. In a 15-minute engagement, this was an extraordinarily efficient expenditure. Pre-war, estimates suggested that scoring decisive hits on a cruiser-sized target at maximum range might require 200 shells or more. The Japanese had built their battleships differently. The Yamato class, the pride of the fleet, mounted 18-inch guns, the largest naval rifles ever put to sea. Each shell weighed 3,200 pounds, heavier than anything the Americans could fire. And the theoretical maximum range was slightly greater than even the Iowa class. On paper, the Yamato-class ships outgunned anything afloat, but range without accuracy is just wasted ammunition. And the fire control systems on Yamato and Musashi, while sophisticated by the standards of optical rangefinding, were a generation behind American radar-directed systems. The Japanese had radar, but it wasn't integrated into fire control the way American systems were. Radar data had to be manually entered into the fire control calculations. This took time, precious seconds that, at maximum range, could mean the difference between a hit and a miss. More critically, Japanese naval doctrine had never emphasized long-range gunnery. The decisive battle, the Kantai-Kessen they had trained for, was expected to occur at closer ranges, 10 miles, 12 miles, distances where optical rangefinders worked well and where crew training and fighting spirit could tip the balance. Engaging at 20 miles wasn't just difficult, it was considered wasteful. Better to close the range, they believed, and fight where Japanese superiority in night fighting and torpedo tactics could be brought to bear. Truk shattered this illusion, but by February 1944, illusions were all Japan had left. The strategic situation in the Pacific had already turned decisively against them. Guadalcanal had been evacuated a year earlier. The Central Pacific Drive was underway. The Marshall Islands had just fallen. Truk itself, once considered impregnable, had been bypassed and neutralized in a single devastating strike. And now, even in surface combat, the one arena where Japanese naval officers still believed their battleships might prevail through superior training and fighting spirit, American technological superiority had proven overwhelming. Ships firing from beyond visual range, hitting targets with a precision that seemed almost supernatural. It was, to officers who had spent their careers training for close-range gunnery duels, a bitter revelation. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. After the engagement, Task Group 50.9 returned to the fleet. The butcher's bill was tallied. American losses, 0. Not a single hit sustained. Not even a near miss that caused damage. Japanese losses, 3 warships sunk, 1 damaged and barely escaped. Over 800 Japanese sailors dead. The material victory was significant, but the psychological impact would prove even more important. News of the engagement filtered back to Tokyo through surviving crew members of Nowaki and through Japanese coast watchers who had observed parts of the action. The reports were confused, fragmentary, but one fact stood out. American battleships had engaged at ranges Japanese doctrine considered impractical, and they had scored hits, quickly, efficiently, devastatingly. For Japanese naval planners, this was deeply troubling. They had known, theoretically, that American technology was advanced. They had known their industrial capacity dwarfed Japan's, but the assumption had always been that in actual combat, factors would even out. Japanese crews were more experienced. Japanese fighting spirit was superior. Japanese tactics, developed through years of rigorous training, would compensate for any material disadvantage. Truk demonstrated that this was wishful thinking. Superior fighting spirit couldn't compensate for being hit by shells fired from beyond visual range. Excellent crew training didn't matter if the enemy could calculate firing solutions faster and more accurately than any human crew could manage with optical sights alone. And superior tactics were meaningless if the enemy could engage at ranges where those tactics couldn't even be employed. The engagement also highlighted another, even more fundamental problem. By February 1944, Japan had already lost the naval war, not in the sense of a single decisive battle, but through attrition, through the steady, grinding destruction of their merchant fleet by American submarines, through the loss of carriers at Midway, the Solomon Islands, and the Philippine Sea, through the loss of trained pilots, which couldn't be replaced at anything approaching the rate the Americans were producing new aviators. The Battle of Truk, if it can even be called a battle, was a footnote. 3 Japanese ships sunk, strategically insignificant, but symbolically it was devastating, because it proved that even in surface combat, even in the arena where battleships were supposed to reign supreme, American technology had rendered Japanese numerical and qualitative advantages meaningless. Let's talk about those Iowa-class battleships, because understanding what they were, and more importantly, what they represented, is crucial to understanding why Truk mattered. USS Iowa, BB-61, was commissioned in February 1943. She was the lead ship of her class. 6 ships were planned. 4 were completed: Iowa, New Jersey, Missouri, and Wisconsin. 2 were cancelled before construction finished. They were the last battleships the United States Navy would ever build. They were fast, 33 knots, faster than most cruisers. This speed came at a cost. To achieve it, the hull had to be long and relatively narrow, 887 feet long, but only 108 feet at the beam. This gave them a sleek profile, but it also meant they were less heavily armoured than the preceding South Dakota class. The armour was carefully designed, concentrated on vital areas. The main belt was 12 1/4 inches thick. The turret faces were 17 inches, enough to protect against 16-inch shells at most combat ranges, but not invulnerable. The main battery was 9 16-inch, 50 caliber Mark 7 guns. The designation 50 caliber means the barrel was 50 times the diameter of the bore. 50 times 16 inches equals 800 inches, or 66.7 feet, nearly 70 feet of rifled steel barrel. Each gun weighed 267,900 pounds with the breech mechanism, over 120 tons. They fired 2 types of shells, the armour-piercing Mark 8 at 2,700 pounds and the high-capacity Mark 13 at 1,900 pounds. A full broadside, all 9 guns firing simultaneously, through nearly 12 tons of steel and explosive. The rate of fire was approximately 2 rounds per gun per minute, though in practice, sustained fire was slightly slower due to the time needed to reload the massive shells and powder charges. The powder charges themselves were remarkable. 6 silk bags per gun, each containing 110 pounds of smokeless powder. The bags were handled with extreme care. Any spark, any static electricity, could cause a catastrophic explosion. The powder was sensitive enough that temperature variations had to be accounted for in the firing calculations. Warmer powder burned slightly faster, altering muzzle velocity and thus range and trajectory. The secondary battery was 25-inch, 38 caliber dual-purpose guns. These could engage both surface targets and aircraft. At nearly 9 statute miles range, they could hit destroyers or shore targets, and with proximity-fused shells, they could create airbursts deadly to incoming aircraft. Rounding out the armament were dozens of 40mm Bofors and 20mm Oerlikon anti-aircraft guns. But the real weapon, the system that made everything else possible, was the fire control. 2 Mark 38 directors controlled the main battery. Each director contained a Mark 8 fire control radar and a complex optical rangefinder as backup. The directors fed data into the Mark 1A fire control computer, a mechanical analog marvel weighing several tons and containing thousands of precisely machined gears, cams, and linkages. The computer solved differential equations in real time. It calculated the ballistic trajectory of shells in 3 dimensions. It accounted for the curvature of the Earth, the Coriolis effect caused by the planet's rotation, air density variations at different altitudes, the drift of the ship caused by wind and current, and critically, it predicted where the target would be by the time the shells arrived. This was revolutionary. Previous fire control systems required manual calculation and constant adjustment. The Mark 1A did it automatically, continuously, updating the firing solution several times per second. The result was that Iowa could fire accurately at targets she couldn't even see with optical rangefinders. In fog. At night. Beyond the horizon. As long as radar could detect the target, the guns could engage it. The engagement at Truk demonstrated this capability in combat for the first time, and it terrified the Japanese, because they realized that their most powerful battleships, Yamato and Musashi, despite their heavier armor and bigger guns, couldn't match this. The biggest guns in the world were useless if they couldn't hit what they aimed at, and the thickest armor was meaningless if the enemy could fire accurately from ranges where return fire was ineffective. But here's the deepest irony. The one that makes this story not just a tale of technological superiority, but a parable about the nature of warfare itself. By the time Iowa demonstrated the supremacy of radar-directed gunnery, battleships were already obsolete. The engagement at Truk was the only time Iowa or New Jersey ever fired their main guns at enemy surface vessels in anger during World War II. The only time. Aircraft carriers had already proven themselves the decisive weapon. At the Coral Sea, at Midway, at the Philippine Sea, at Leyte Gulf, the largest naval battle in history, battleships fired their guns. But the battle was decided by aircraft. By 1944, the battleship's role had been reduced to shore bombardment, anti-aircraft escort for carriers, and occasionally, as at Truk, hunting down damaged or inferior enemy vessels. The Iowa-class ships were, in a sense, the ultimate expression of a dying weapon system, faster, more accurate, more sophisticated than any battleships that had come before. But still battleships, still tied to a mode of warfare that aircraft had rendered obsolete. They were magnificent anachronisms, built to fight a war that no longer existed. This is what the Japanese admirals never fully understood. It wasn't just that Iowa's guns could hit from 23 miles. It was that hitting from 23 miles didn't matter anymore. Not when carrier aircraft could strike from 200 miles. Not when a single carrier could project more destructive power than an entire battleship squadron. The question wasn't whether Japanese battleships could match American battleships in a gunnery duel. The question was whether battleships mattered at all, and the answer, by mid-1944, was increasingly no. Yamato and Musashi would both be sunk by aircraft. Yamato, in April 1945, on a one-way suicide mission to Okinawa. Musashi at Leyte Gulf in October 1944. Neither ship ever engaged an enemy battleship. Their massive 18-inch guns, the most powerful naval artillery ever mounted on a warship, fired at aircraft, at destroyers. But never at the American battleships they were designed to destroy. The Iowa-class ships had longer careers. They were reactivated for Korea, where they provided shore bombardment. New Jersey saw service in Vietnam. All four were brought back into service in the 1980s, modernized with cruise missiles and anti-ship missiles. They fired their guns in combat for the last time during Operation Desert Storm in 1991, when Missouri and Wisconsin bombarded Iraqi positions in Kuwait. But even then, they were relics. Impressive relics. Floating museums of a bygone era. The cruise missiles they carried had longer range and greater accuracy than their 16-inch guns. The aircraft flying from carriers hundreds of miles away delivered more ordnance more precisely. The battleships were kept in service partly for shore bombardment, partly for intimidation value, and partly because no one quite knew what else to do with them. Now, all four are museum ships. Iowa in Los Angeles, New Jersey in Camden, Missouri in Pearl Harbor, appropriately moored near where the war began. Wisconsin in Norfolk. Visitors can walk their decks, stand in the turrets, marvel at the machinery. But the era they represent is gone. The age of the battleship ended not with a dramatic last stand, but with a quiet acknowledgement that other weapons were simply more effective. The engagement at Truk stands as a peculiar moment in this transition. A demonstration of technological superiority in a weapon system that was already being superseded. Japanese admirals were shocked that Iowa could hit from 23 miles, but they should have been more concerned about the carriers that had destroyed 250 aircraft and dozens of ships earlier that same day. Still, for the men who served on Iowa, for the crew who loaded the shells and fired the guns and maintained the machinery, Truk was proof that their ship, their weapons, mattered. That they weren't just along for the ride while aircraft did the real fighting. For 90 minutes, on February 17, 1944, battleships were relevant again, guns mattered, and the skills and systems they had trained on, the massive technological apparatus of radar and computers and precision engineering, had proven themselves in combat. Captain McCrea wrote in his action report that the engagement demonstrated the effectiveness of radar-directed fire control at extended ranges. He noted that Katori had been quickly destroyed despite her attempts at evasion, and that the Japanese return fire had been ineffective. He recommended that future surface engagements employ maximum-range radar-directed fire as standard doctrine. His recommendations were noted, and then quietly filed away, because by the time the report reached Washington, planners were already focusing on the invasion of the Marianas, on carrier operations, on submarine warfare, on everything except battleship versus battleship combat, which seemed increasingly unlikely to ever occur again. For Japanese, the lessons of Truk were learned too late to matter. Reports reached the Naval General Staff in Tokyo. Engineers studied what little information could be gleaned from survivors. They understood, finally, just how far behind they had fallen in fire control technology. Plans were drawn up to retrofit Japanese battleships with improved systems, but by early 1944, Japan lacked the industrial capacity, the resources, and most critically, the time to implement such upgrades. The war was already lost. Truk had demonstrated it, not because of the 4 ships sunk, but because of what those sinkings represented. American technology, American industry, American systems were superior across every dimension of naval warfare. Fire control, radar, damage control, logistics, industrial production, pilot training, code breaking. The Japanese could still fight. Their sailors were still brave. Their ships still dangerous. But bravery and danger couldn't compensate for systematic, overwhelming superiority in every measurable category. One Japanese naval officer, interviewed after the war, described the feeling when news of Truk reached fleet headquarters. "We knew then," he said, "that we were fighting a war we had already lost. Not just the battle, but the war. They could do things we couldn't do, build things we couldn't build, and they could do it faster and better. We had hoped that fighting spirit would compensate. After Truk, we knew it wouldn't." This realization spread through the combined fleet, not all at once, not uniformly. Some officers still believed in the possibility of a decisive battle. Some still thought that one great victory, one crushing blow, could force the Americans to negotiate. But increasingly, the prevailing mood was fatalistic. The question wasn't whether Japan would lose, it was when, and at what cost. The final tally from Operation Hailstone makes for grim reading, from the Japanese perspective. Over 200 aircraft destroyed. 3 light cruisers sunk. 6 destroyers sunk. Numerous smaller warships and auxiliary vessels destroyed. 32 merchant ships and transports totaling over 200,000 tons sent to the bottom, all accomplished in 2 days. With American losses of 21 aircraft and approximately 100 casualties, Truk, once considered the Gibraltar of the Pacific, was rendered useless. The garrison remained, cut off, starving, until the end of the war. But as a functioning base, it ceased to exist on February 18, 1944, and the surface engagement, the 90-minute gun battle that sank Katori and Maikaze and demonstrated the Iowa-class battleship's capabilities, was almost forgotten in the larger destruction. Almost, but not quite, because for the men who served on Iowa and New Jersey, for the officers and crews who had loaded those shells and fired those guns, and watched through binoculars as enemy ships burned and sank, it mattered. It proved that their ship, their weapons, their training had value. That even in a war dominated by aircraft carriers and submarines, there was still a place for the big guns. They were wrong, of course. History would prove them wrong. But in that moment, in the waters northwest of Truk, with smoke rising from the lagoon behind them and the record for longest-range naval gunfire engagement set and likely never to be broken, they had every right to believe they mattered. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.